I want to talk about complexity, right? We have complexity that occurs in our lifetimes, in everything that we do, in everything that we build. A lot of that complexity is inherent. It is inherent to business logic. It is inherent to even potentially physical systems that we model, and it sort of exists and there's nothing we can do about it. Then there's complexity that we just stupidly introduce because we make the wrong technical choices, we make the wrong platform choices, etc., etc. It's our fault. We could have made it simpler, but we didn't. But then there's a third category of complexity. This is complexity that we lie to ourselves about. Complexity that we think just needs to be there, but really doesn't. And when we analyze the technical choices that we have at the end of solving something compared to what we knew at the beginning of it, we typically say, why the heck did I do that? And, this happens in architecture all the time because, of course, when you're architecting a project, you typically know least about the requirements because you tend to find out the requirements as you work on something, right? Because we're all really good at gathering requirements, right? Nobody's ever had last-minute requirements come around, right? So as that whole process happens, we tend to lie to ourselves about, oh, this is minimally complex, or oh, this could have been easier, but actually it couldn't have been. And I think this third category is actually most of the complexity that exists within business logic goes into this third category, a category that we end up lying to ourselves about. And I think actually the older we get, the more we lie to ourselves about it. So I want to talk about lies we tell to ourselves about complexity, or pathodental complexity. The dental is because we lie to ourselves through our teeth about it. So the first, I think these are the two biggest that we see in functional programming. The first is that we have to crush all boilerplate. We have to get rid of all boilerplate. Boilerplate is inherently evil. And the second one is that, once you understand this minimal set of concepts or ideas, functional programming is incredibly easy, and there's this magical point at which everything sort of occurs. I think these are two great pathodental lies that we tell ourselves, and I want to go into them. But first, I have to tell a story. I have to tell a story in order to give any of this meaning or relevance. So the story that I'm going to tell is the story of engineering, right? We always want to use the latest and greatest technology. We always want to use the latest and greatest platform, and business logic doesn't automatically follow our wishes. It exists encoded in whatever form it's encoded, and we just have to deal with it. So, okay, let's move everything to the latest and greatest platform, right? We've all been there thousands of times, and here's what the product owners are thinking. Holy crap, we're going to get half of this wrong, right? Part of it is intrinsic risk of the new platform not working, but typically, we can make enough POCs to actually convince people and ourselves that the new platform is going to work. But then there's all of the issues that can go wrong with the business logic being migrated from platform to platform. And that's what product owners are really scared of. So there was this insight they made at Morgan Stanley almost a decade ago now. Disclaimer, I don't work for Morgan Stanley. All opinions expressed are my own. No pigeons, squirrels, or dung beetles have been harmed in the making of this presentation, et cetera, et cetera, et cetera. Now, they had this insight that basic math is representable in just about any language, I think, right? But why not business logic, right? Business logic ultimately does not really need polymorphism, or at least parametric polymorphism. It does not need a lot of the features that exist within languages. Why can't we have business logic be cross-representable across different languages like basic math, right? Well, there's a problem, right? We have to represent it in some kind of syntax tree. What are the features available to encoding this business logic in a cross-platform way? The only reason that math is cross-platform or cross-language is because every single language's independent syntax tree happens to support this kind of mathematical reasoning. but not the same is true of business logic, right? You need some kind of tree in which to encode this business logic. You need a business logic specific syntax tree, right? You need to encode this into some kind of tree that is specifically for the business logic. And okay, what is that? What is that tree? Well, we have to figure it out. Okay, so if we do figure that out, then yay, we can migrate our business logic from potentially, the language in which we write it to any other language, quote unquote. So if we can do that, then we can actually transpile business logic from one language into another, and then we can achieve this wonderful independence and, move to whatever latest platform we want and not have to worry about messing things up. So that's why you can call this business logic format an intermediate representation, or an IR, because it potentially moves us from the host language in which we build it into some other language or platform. Now, in order to actually have that done, right, we need some kind of macros or compiler magic. We need a way to capture the local syntax tree, right? This guy here, right? We need to capture it somehow, right? You can't just write, 1 plus x inside of a language and have that actually be captured somewhere. You need to be the compiler in order to actually capture it. So, okay, we need some compiler plugins or some macros or some other sorcery to do that. Fine. Now, if we want to encode business logic, what features should this format have? Right? And the first answer is going to be object-oriented programming, right? That's the oldest thing. Everybody knows it. Well, here's the problem, right? Object-oriented programming is very good about capturing mechanism, right? This is all mechanism. What the hell is this thing actually doing? Right? We have to read it, figure it out, bang our head a little bit. Okay, here's how you do the same thing in FP. Right? This is Elm or F# and that whole family of languages, right? Compare this to this. Right? This is much closer to the intent. Right? We're just capturing the total quantity and we're finding the biggest supplier. Right? This is an encoding of intent, much more than this. So, okay, let's think about FP. Let's think about using FP features to capture intent. All right, so that means that our business logic tree has to use FP features, and if we can actually find the FP features that are common in every single FP language, okay, assuming that we can do that, then we can achieve this cross-platform ability of our business logic. And this was what the people at Morgan Stanley came up with. This is how they created this Morphere project, where they essentially said, look, it's all about this intermediate representation. It's all about the intermediate representation that allows us to capture the business logic and transport it from one form into another, into another, into another. Okay, wonderful. And, all the ideas that I'm going to talk about, at least in the first part of this presentation, are from this FinTech Open Source Foundation ordained family of repositories. Okay. Now, what do you need to be able to capture inside of a syntax that allows you to cross-platform business logic from one FP language into another? All right, well, you need some way of capturing something that can be many things, i.e. co-products. We call it enums, right? We need some way to capture something that has fields inside of it, i.e. records, right? There's how you would do it in a ML-style language above, and there's how you would do it in Scala below, right? This is Scala 3 syntax. In Scala 2, you do sealed traits. Wonderful. And we also need to encode logic, right? There's a syntax for branching, there's a syntax for function definitions and variables, et cetera, et cetera, et cetera. And if we just figure out how to encode all of these other things, and it's only 9 or 10 things you need to encode inside of a syntax tree, then you can achieve a language-independent encoding of business logic. Okay, great. And there are a bunch of details that we have to figure out because, life, but fine, let's assume we figure this out, and then we have our wonderful cross-platform ability, and we can transpile our business logic from any language into any other language and potentially future-proof our business logic, because tomorrow we know that there will be wonderful new platforms that we will want to migrate to that we do not know about today, and then we can, write new transpilers and transpile our business logic to them. Wonderful. Now, the first part of this is actually modeling the data structures that it takes to encode this wonderful intermediate representation. And here's where all the wonder starts coming out. All right, let's encode basic primitives, and that's what we would do with them. By the way, we typically want to have some kind of more abstract structure in order to be able to encode the native primitive, right? It's a integer that wraps a real Scala integer. We would have to have equivalent structures in F# or in Elm or whatever other FP language we want to encode this to. And all right, great. So we encode primitives. And by the way, remember this. This will be relevant later. We need to encode enums and records. OK, fine. So that's what it would look like in Elm and Scala. Those are the actual values. That's how it would look like in Scala. And we achieve, at least in terms of enums and records, some cross-platform ability, we think. And there's how you would actually model that using real case classes, right? So we model them like so. Another interesting thing is that we want to be able to capture schemas, right? The wonderful thing about encodings like Avro is that you actually want to know all of the different things that something can be. This is a really big problem, by the way, with encoding formats like, Amazon Ion that actually can't support enums because it's supposed to be freeform. It's supposed to be semi-structured data. You can't encode an enum with semi-structured data. Right? That's a problem. OK, so how do we resolve that? We can encode the schema on every single object. All right, wonderful. So we need to have a model not only of data, but a model of schema. Wonderful. OK, how do we do this? In Scala, generic derivation magic. We use a bunch of macros, right? Scala 3 generic derivation or Magnolia or whatever it is. We take our types, we shove it into our generic derivers and outcome constructors that we can then stick instances to, and then they construct this stuff here below. All right, wonderful. Now, we build all of that, right? We construct all of it, and wonderful. Now, I was a little bit vague right here about what this actually is. What are these fields? Account number data, customer ID data. What the heck is that? What kinds of things plug into there, right? Are they simple integers? Can we do that? That seems to be fine, except for the fact that what are the problems, right? You can flip them, right? You can easily mess this up, just like you can mess this up in your code. You can mess this up in your model. How do we guarantee that these field types are not messed up, right? What is an account number? What is an account number? What is a customer ID? Right? And we typically say, new types, right? Write a case class that extends any val or an opaque type, or use some other library to model a new type and model a new type. Wait a minute, we want this to be cross-platform. We want this intermediate representation to be cross-platform. How the heck do you new type this? We don't have classes anymore, right? We said we want to have a basic IR. We don't want to have all of these wonderful things in which we encode new types. How the heck do we do that? OK, well, here's an enum. We can have a single instance enum. Right? We have a single instance enum which encodes our new type, and then we create the instances like this. OK, account number dot account number. Weird, but OK, fine, it'll work. All right, and here's how that data will be modeled. Wonderful, except that, by the way, there we go. There's our generic derivers, except that nobody actually encodes data this way. Right? Have you ever seen someone in Scala ever do this? No, this is a fantasy. Nobody actually does it. Here's how we do new types. One of 10 different ways, right? Scala 2, Scala 3 opaque types, CO prelude, the Estasio library. You could use refined or 10 other ways to do it. OK, so we can't do this automatically. How do we solve this? We solve this with generic derivation. OK, now we have to bring it on the user to actually write their generic derivers. Wonderful. OK, well, here's what the user has to write in order to do that. OK, even better. And they have to do this for every single new type. They have to write a generic deriver like this. OK, wonderful. Right? Oh, they could just use Copilot. Right? We want to impose on the user to use Copilot. Wonderful. Right? OK, now let's see. We can simplify it. We could write some helper classes. OK, wonderful. That's what we want. We want it to be a one-liner, right? We could rely on the user to build a one-liner. we can have the user have a one-liner, and with that one-liner, they can construct a new type for every single new type class that they need to have. Okay, great. What does it take to actually implement this on the back end? All right, well, we need these kinds of overridden methods, right? This is Scala 3, so you need to have a target type annotation or a dummy implicit in Scala 2 or some other sorcery in order to get this thing to not complain about the erasures being identical, blah, 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 blah. But fine, we have these overridden methods, it works, and we need to have this for every single Scala primitive. And potentially more kinds if we want to encode dates in our cross-platform IR and other potential numeric types and God knows what else. And each one of these is one of these, and this is what our library needs to do. And at this point, our Scala brains give us a bunch of bloodlust and, down with the boilerplate, crush it, destroy it, right? And here is where we get to our great pathodental lie that we have to crush the boilerplate. All right, let's go with me. Let's crush the boilerplate. Okay. We don't like this, so let's use type classes. Let's use type classes. Let's encode them into a type class instance. Ooh, little problem here. Let's see that down here. You encode the stuff with type classes. See this data.int.int thing, right? We didn't have that before. When we had our boilerplatey solution, you didn't require the user to specify those. Okay, we don't want these additional details to bleed into the user API. Okay, so we can use some more advanced techniques. Let's turn this object new type enum into a class. Let's encode the type on that. Oh, and then we also have this wonderful type constraint. Remember I told you to remember this earlier? This wonderful type constraint up here that allows us to not have to specify that, and that plugs into the other type class instances, and then that dot value thing plugs in the type, and then because we have the type available there, the Scala type system can then infer that. Wonderful. So this is type classes and type level search, and yes, we've already crushed 60% of our boilerplate. Not just type classes, but type classes with type level search. Okay, wonderful. Oh, but wait a minute. We don't like these giant type class construction pieces of logic down here, the ones in gray, right? We don't like any of that. We want to get rid of that too. Okay, so what do? We want to have indirection. We want to have type classes, type class constructors. Wait a minute. We have type class constructors with this new type enum over here. We need two levels of type class constructors. Type class constructors that lead to type class instances that lead to more type class constructors that lead to more generic logic. Okay. Wonderful. But guess what? We've killed 80% of our boilerplate. All right. Okay, but we can go even further. All right, we can go even further. We can introduce type level logic. We can introduce a type level class that is a type level constraint. And then that type level constraint, oh, CB had this second parameter down here that we needed to specify for every single type class. Our constraint allows us to plug into this data.basic constraint that we had before, and then we don't even need to do that. 80% of the boilerplate crushed. Sorry, 85. 85% of the boilerplate crushed. Okay. All we need to do is use type classes and type level search and type class constructor and type level functions. But am I wonderful, right? But we got rid of all of our boilerplate. Now, before I show you my next slide, I have to warn you. This contains guesstimation, crude, vulgar, explicit guesstimation. Take all the numbers I'm about to show you with a grain of salt. Viewer discretion is advised. I would not show the next slide to all audiences. I believe we here at Functional Scala 2023 are a mature audience, and I believe that we can stomach what I'm about to show you. This is not for all audiences. If you have delicate sensibilities, please avert your eyes. What are the amount of programmers in the world that can actually maintain all of these techniques? Okay, this is very much back of the envelope calculation. I can show you the methodology. It is very crude, but think about it. How many people are there in the world on which you can actually drop a code base with type classes and type level search and type class constructors and type level functions? I don't think there are more than 60,000, 100,000, not more. Okay, but here's the thing. Not everybody here is on the market at the same time, right? With programmers, if you've got a 1.5% unemployment rate, here's how many people that are on the market at the same time. Here's your hiring pool. Okay, there's your hiring pool. Now, okay, fine, all small or medium, even medium-sized programming language communities have this problem. But the point is that if you simply settle for some boilerplate, and if you simply use some simple techniques, literally thousands of times more people can maintain your code. Thousands of times. Okay? So yes, we've crushed all of our boilerplate, but who can maintain the solution? Okay, and like people are gonna call me anti-intellectualist for saying this, whatever, or some other jargon that I've never heard of before. But you have to think about this. It is irresponsible to not think about this and not think about the maintainability of what you're doing. Because guess what? You might have to just maintain this forever, and you might not want to do that. So, and for each one of these levels of complexity, we can lie to ourselves about how it's intrinsic. Oh, we need all of these features. Oh, we need type classes. We need type search. We need type class constructors, multiple indirection, and type level functions. We need all of this stuff, right? Because otherwise we'll have all this horrible boilerplate. At each level of complexity, we're very good at convincing ourselves why we need that complexity. That's the way it works, right? We're very good at convincing ourselves. Again, the older we get, the better we are at it. Well, here's what I chose. Again, you don't have to choose that, right? You can choose anything along this spectrum based on your team's ability, based on your development culture. You can choose any one of these things and still be able to have potentially hundreds of times more people maintain your code base. For this particular thing, that's what I chose. Screw it. The library author can do Copilot. I'm not leaning on Copilot, not forcing it on the user, not forcing the user to write boilerplate. I'm forcing the library author to write boilerplate. And I think it is a worthy sacrifice in order to do that. This is fine. You can have the library author deal with boilerplate, with repeating the same thing 30 or 40 times for particular code bases in particular businesses to solve particular problems. That is a hit that you can take. This is not a library that I'm maintaining in open source necessarily, or even if it is, this is not something that I want to maintain for my whole life, so I can just deal with that. And that brings me to a second pathodental lie. Second pathodental lie that we tell ourselves, that I've told myself all the time, when I'm looking at code bases that have not made this choice to keep things simple. And sort of the message that we keep telling ourselves, or that I've kept telling myself, is, oh, this is just simple. I just need to learn a few basic concepts and all of this will become simple, right? And this started happening years ago when I was first learning Scala. I mean, again, it's very different. We have a lot more literature, et cetera, et cetera, et cetera. But this was like 7-8 years ago when I first started learning Scala. Well, more than that, actually. I'm getting old. Anyway, everything was like, learn this holy functor hierarchy tree, and then you'll be able to understand everything. Okay, how do you learn programming? How do you learn programming? Any kind of programming. Well, you learn design patterns. Either you see design patterns used in real code, or you learn them from a book. But either way, you learn design patterns, right? And that's how you learn programming. Okay, but these aren't design patterns. This tree is not a design pattern, right? This is like some pseudo-mathematical set of axioms encoded in a pseudo-mathematical tree. These are not design patterns. What are the actual design patterns, right? And then I start looking at real Scala code. I'm like, what the hell? I can't understand any of this. I've memorized this functor hierarchy tree. I understand what all the concepts in there entail. Why the heck can't I actually understand any real Scala code? Again, what are the design patterns used here? Right? And then I saw this slide. I think we've all seen this slide at one point or another. Right? A lot of people like to share this slide because it's funny. Well, I made the mistake of actually taking this slide seriously. I'm like, yeah, functional programming. We don't need any design patterns. Who needs design patterns? We have nested functions. And this slide screwed me up for years. This slide is complete and utter nonsense. This is completely untrue. Okay, this is like a Far Side joke, right? Where income type classes, outcome products, and some kind of magic happens in between. I just don't understand what it is yet. Okay, this slide is nonsense. Here's the reality. Okay, we do have design patterns. Not only do we have design patterns in functional programming, we probably have more design patterns in functional programming than object-oriented programming. We just don't have names for all of them even. Okay, oh yes, here's some more detail. Oh, and there's some more. There's some more. For every single design pattern in object-oriented programming, I could probably give you a similar design pattern in functional programming. They do not map one-to-one necessarily, but every single one has a corresponding design pattern. And I want to talk about three of them in particular that of all the ones that we have. Let's talk about the great and awesome adapter pattern. All right, here's an adapter pattern. Let's look at some Java code here on the left-hand side. Okay. All right, we have some kind of data model. We want to have a new type, which is this user ID, and we want to encode this into JSON. Let's use Google JSON, the JSON library. Oh, whoops, we don't want to have this inner nested type here, right? We don't like that. We want to have the actual value, right? We don't want our new types to be encoded into our JSON hierarchy. What do? We write this adapter. Right? We have our adapter that we write. We plug our adapter into our JSON builder, and voila, the value is right. Okay? So we wrote an adapter. Wonderful. We used the great adapter pattern. How do we do this in Scala? All right, here's our model. Here's our serializer. Right? Same problem. We have this nested value. What do we use? ContraMap. Right? The great ContraMap. Right? Okay, we use our ContraMap our values right? The same thing that we did with our OOP serializer. We pull the value out, we stick it into a primitive value, and voila, the value is correct. Okay, great. Let's look at this in a bit more detail, and let's take out the extraneous stuff. Wait a minute. We did the exact same thing. This is the exact same crap. Literally the exact same thing. Right? A ContraMap is an adapter. Right? We just say, now you can stick a new type in. Not a new type, an actual new kind of thing in. Right? You stick a new kind of thing in, it maps to the old kind of thing we had, right? We had an encoder for a string. Now you can stick in a user ID, it'll do the same thing. An adapter is nothing more than a ContraMap. Let's look at another one. The great strategy pattern, right? Here's a strategy pattern. Let's do something trivial like color a string. Right? We want to have a string be a particular color. So what do? We use a strategy pattern, excuse me. There's our user API. We push in the strategy, right? Color strategy dot blue. We use the strategy pattern, and out comes our string. Okay, so how do we do this with functional programming? Well, there are a bunch of ways. We could do the exact same thing. Literally, we could do the exact same thing in functional programming, but let's think a little differently, right? Now, starting like Scala 2.12, you can actually pass in static objects. which means you can actually pass in a lambda, i.e. you could just do that, right? Underscore dot blue, and you just use a lambda. And you can use any color you want that is available in this ANSI color object. You just use a lambda, okay? So a lambda is actually the ultimate strategy pattern, right? The lambda says, use this logic, plug in the user logic here. The lambda is the most powerful form of strategy, right? The lambda strategy, the anything strategy. Now, okay, fine, you can say this is too powerful, we want a recommended list of colors that you could use for the string. Okay, well, here's a very frequent design pattern that we see in functional programming. We have a custom strategy into which you pass your lambda, right? And then you can have both. You can have the normal things, and then you can have custom injectable user logic. I see this all the time in code bases. Okay, so a strategy is actually a minimal form of a higher order function. Finally, let's look at the great visitor pattern, right? This is something that really over my career has haunted me. All right, the great visitor pattern. Okay, let's look at intermediate representations. Everyone's talking about Kotlin these days. Let's look at the Kotlin encoded intermediate representation, right? We have this block over here, right here, person.name.first, p.name.first. Well, there's how it's encoded in the Kotlin compiler's intermediate representation. I want to convert this into my intermediate representation because I want to be able to capture the meaning of this. I want to write some compiler plugin. Okay, so what do I do? What do I do? I have this visitor. This visitor that takes in every single kind of thing that this IR element can have. And I need to use these two particular methods when I implement this visitor pattern. I implement this visitor pattern with these two particular things. I use the accept method. The accept method then calls the IR elements visitor accept method, recursively calls its accept method chain, and voila. Wonderful. I have an output my own syntax tree. Okay, great. All right. Is this essential complexity? Is this essential complexity? Talk to any Java person. Oh, very essential. Well, how else would you do this? How else would you do this? How else would you do any of this? Well, like that. That is literally all you need to achieve this. This is all you need. Right? Recursive pattern matching. Right? It's actually that simple. This actually does the same thing as this. Believe it or not. Is the exact same thing. Okay? And, oh, yes, 20 years later. Thank you, Java. 20 years later, you figured this out. All right. Plagiarize, plagiarize. Let no one else's feature set evade your eyes. Right? Thank you, Java. Oh, yes, and now we even have underscores for variables we don't care about. It gets better and better and better. Okay? Meanwhile, has Kotlin done this? No. Birds chirping on supporting complex pattern matching for years now. I wrote a library just because I was fed up with this. You can look this up. This is extremely limited. It only allows 2-level nesting in 2 variables, but if you ever happen to be afflicted with the need to use visitor patterns in Kotlin, you can have a look at this. But anyway, recursive pattern matching is how we do a visitor pattern. It achieves the same damn thing. If you have recursive pattern matching, you do not need visitor patterns. So long as you can actually pattern match on stuff and that construct actually exists in your language. Right? All you need to do is write a recursive pattern matcher, and you do not need these stupid visitor patterns. Like everything that JetBrains has built inside of their PSI trees And their entire technique that they have, the entire visitor pattern, you actually don't need if you have recursive pattern matching. All of that stuff is actually not necessary. You look at the reams of code, thousands of lines of code that have been built to have these extremely customized visitor patterns, and then you realize none of that stuff technically needs to be there. And that might drive you to insanity, so be careful before you actually do that, but it is very much the case. Conclusions. I think I'll wrap this up. Boilerplate is not necessarily always bad. If you consider the fact that potentially thousands of times more people can maintain your code base, if you have a little bit of boilerplate, and functional programming has plenty of design patterns, and we should actually talk about them and talk about the design patterns that we use in functional programming, because they are plentiful, and a lot of them are very interesting. There are a lot of other pathidental lies that we tell ourselves that I could have talked about, but I'll save you the headache in the interest of time. And sort of my take-home message is, we don't know what complexity is intrinsic and what complexity is essential, right? All complexity is intrinsic until we've learned a better way to do something. And that's it. There are the links up here. That's this presentation. You can check out this library. Also, some upcoming features in Quill happening too. So, thank you, everyone. Have a wonderful conference.